All right, well, we covered a lot of ground, but to kind of ramp up this first part of our simulation module, I just want to talk about, you know, our clinic opens and closes every day. So clearly we can't just run it one time, right? And so the type of simulation where we've got something that kind of starts and ends, um, we call these things terminating simulations. And so to be able to kind of get representative samples from simulating the system, we need to run it multiple times. So instead of just running our clinic one time and looking at the at the output statistics, we run it a whole bunch of times, and then we can process those multiple runs. It will give us much better estimates of our various performance metrics. So what I've done is with one of the future versions of the model, I did this scenario that we just looked at. I ran it 15 times, 3 greeters, 3 reg staff, 15 vaccinators, and 3 scheduling staff. And the version of the model that I used to run it actually creates a CSV file that has the detailed patient logs for each replication. So I'm going to show you what it looks like, and we'll see in the next part of the module how to actually do this, how to create our own. So this guy is the consolidated clinic patient log. And notice I'm kind of naming it now with a scenario. This is like the base scenario, and this is the capacity plan part of the scenario. 3 greeters, 3 reg, 15 vaccinators, and 3 schedulers. So again, this is just ways of me starting to be able to keep track of things. But I want to show you what this thing looks like. So notice it's almost 28,000 rows because I've run the thing 15 times. So this is the replication number, and then the first column just has the scenario in it. These are the patient ID numbers and all the timestamps that we're used to seeing. So, and in fact, in addition, it's got all the the computed durations. So this is kind of our main statistics, detailed statistics table. Or actually our timestamps, table. But now we can use pandas, and we could just group by rep num, and we can do, statistics by replication, and then we can do overall statistics. So in the first thing I'm gonna do is I'm gonna do a group by rep number, and let's just look at one of the stats. I'll look at time and system. So here we go. So you can see across the 15 replications, right, there was a different number of patients each time. Those are random. And so you look at these and you'll see that even the mean time in system, like the first simulation replication, the mean time was 50 minutes. And one of these, it was 24 minutes down here in this one. So you can see that the random numbers can really make a huge difference. And that's why we want to do things multiple times. And now what we'll do is we'll take the mean of this mean column to get an overall mean. But we're actually going to go even further than that, right? So whenever we report statistics like the overall grand mean, we really should convey how much uncertainty we have. And if you remember your statistics, we do this through confidence intervals. So what we're going to do is we're going to create an approximate 95% confidence interval on the mean time in system. So again, we're putting a range on the mean. Okay, we're literally none of these other columns matter. All we're doing is we're putting a range on you can see why we need to put a range on it, right? Because it varies, right? It's random because it depends on which replication that we did. So how do we do that? First of all, we compute the overall mean. Let's call that thing y bar. That'll be the mean of this column. And the standard deviation of that mean column, let's call that thing S. So this is not this standard deviation. This is the standard deviation of these means in this second column. And so then our confidence interval is y bar plus and minus 1.96 times the standard deviation divided by the square root of the sample size, which is the number of simulation replications. So in our case, that's 15. And the 1.96, that's the 97.5 percentile of the standard normal distribution, or the Z distribution. And I say this is an approximate confidence interval because we're assuming we can get away with using the Z distribution instead of the T distribution here. And so there's 2.5% above and 2.5% below the minus 1.96. And so that's how we get the confidence interval is a 95% confidence interval. You might also remember from basic stats, this quantity here, s divided by square root of n, we call that thing standard error. And it's also, it is, if you take from the 1.96 all the way through the standard error part, that thing is called the half width, right? Because our confidence interval is the mean plus or minus this thing. So, that's half the width. And what's nice is that we want a small half width. And in simulation, it's kind of easy to do because all we have to do is make n bigger, right? Instead of running 15, I can run 100, right? And then, this will instead of dividing by the square root of 15, I'll divide by the square root of 100. So this thing will shrink. Okay. So just to kind of show those, right? We know n is 15. The overall grand mean is 36.2 minutes, so that's the mean of this column. That looks about right, just eyeballing the numbers. And the standard deviation of that column is 7.3 minutes. And so our confidence interval, 95% confidence interval on the mean is 32.5 to 40, right? So roughly speaking, this isn't entirely correct, but just kind of roughly speaking, we believe that the mean time in system is between 32 and 40, right? 32.5 and 40, and we're about 95% certain. That's where I'm cheating a little bit on the definition of a confidence interval. But what I really want to get across is this is putting a range on the mean of time in system. It has nothing to do with the overall percentiles. Many patients may wait longer than 39 minutes. This is just on the mean. And in fact, if I plot the histogram for time and system, right? I mean, here's 39 minutes over here, right? Tons of people are waiting longer than 39 minutes, right? So this is the whole distribution. Confidence intervals are just around a specific statistic, like the mean of that distribution. All right, so we covered a huge amount of ground in this notebook. Everything from kind of learning the basics of SymPy and then progressively building more complicated models up to our full clinic model, including using object-oriented programming and implementing a vaccine clinic class. Still tons of possible improvements. So let's think about some of these. So one is, it would be, we've got a lot of inputs, right? And at this point, we've hard-coded a ton of things into the model. We put a bunch of, kind of things in that main driver program, such as the number of resources. It would be really nice to somehow be able to specify all of these inputs somehow through a command line interface. Maybe we could have a configuration file that we store them in. Because right now it's really kind of clumsy to have to go through and be editing code to make changes in things like the length of time a certain procedure takes. That's not a great idea. And then also, obviously, all that output work we did, we don't want to be doing that manually. So we want to, bake a bunch of that output processing into the simulation model itself. And then also just kind of thinking about it. Right now, we're modeling this with Poisson arrivals, but really. For example, in the early days of the COVID vaccine, a lot of places were doing things like, giving people a scheduled time. They would literally like be giving, say, 15 people every 10 minutes, giving them you had an 8:10 appointment, but there were 14 other people with you who had that time. So somehow being able to model things like, batch scheduling of appointments and things like that. Okay, so in the second half of this module, we're going to tackle some of these improvements. Especially, we're going to spend a bunch of time learning how to do things like create command line interfaces. It's a nice thing to know how to do. And that, I've included a bunch of, resources below. Some of these I've mentioned above. There's really nice set. These are really long, actually, but they're literally recordings of kind of an online workshop. So they're as long as they're like an hour and 45 minutes each of these. But they're very similar in spirit to what we've done here, kind of building up from very simple models to more complex, and they're actually healthcare related as well. So links to the my two blog posts, and then also this there's a really nice it's a consulting company that does work with network simulations, and they've posted a bunch of their stuff. It's quite nice. So all right, so there's our crash course in SymPy, and then we will in the next part of the module, we will take on some of these improvements.